Hey guys, it's off by one here, and today we're going to be solving find minimum in rotated sorted array. In this problem, we're given an array of length n that is sorted in ascending order, and the array is also rotated between 1 and n times. So in this example here, we're given an array nums that is sorted from least to greatest, but when it's rotated 4 times, for example, we see that the 0 is shifted by 4 spaces. So 1, 2, 3, 4. And that's the new spot of the 0, and then everything that follows after is in regular order. And then if it's rotated 7 times, then that means we basically go around the whole array and then start back where we were. So it looks like the regular array, but it was actually rotated 7 times. And in this problem, they want us to return the minimum element of the array. And that's pretty easy, I guess. All we have to do is run through the array once and just keep track of the minimum, and that would only take us O of n time, which is a pretty good solution. But the problem is that they want us to write an algorithm that runs in O log n time. So what does this mean? Well, let's start by thinking what O of n really means. And when we have an algorithm that runs in O of n, that means we expect n operations to be done before we can find an answer on the average case. So for example here, let's say we go through the whole array, that would be 5 operations. But if they want us to write in log n algorithm, that means that log of 5 would be somewhere around 2. I've written this example here where n equals 8. So for an O of n algorithm, we can expect to have 8 operations. And for an O log n algorithm, we can expect to have a max of 3 operations. So let's just take a look at this array and see if we can find some kind of pattern here. Well, we know we don't care about this second half of the array because we can see that it does not contain the min. So maybe a way to solve it would be to divide and conquer. So let's see if we can split this array up and find the min that way. So we eliminate this half of the array, and we're only looking at this now. And then we can see with our eyes that this half of the array is not very useful, and we can just split it down the middle again and then get rid of that. And then finally we can split the array again and see that our min is going to be 1, and that we don't care about this 2 here because that's not our min. And as you can see, that took just 3 operations. We split the array 3 times and then we were able to find the min. So how do we know which part of the array we don't care about? To start, we're going to have some pointers. We're going to have our left pointer, we're going to have a right pointer, and we're going to have our mid pointer. And our mid pointer is going to be at 4 and not 5 because that's just the way the code works. Whenever you do left plus right divided by 2, is going to round down, and that's why I put it here for now. So what relationship can we notice here? Well, we know that this is already in ascending order, and mid is going to be less than the right if it's sorted correctly. So maybe that can be one of our checks. So what do we actually want to happen whenever this condition is met? Well, we can see that this is the sorted array here, and we're not going to care about this part at all. So what we can do is move this right pointer where the midpoint is. So we can just update this, and then our mid pointer is going to be updated to the left plus right divided by 2, which is going to give us this. And now we can see that if we just keep doing this condition here, we're going to eventually find the min. So let me just show you that. So like we said, we want our right pointer to be updated to our midpoint. And our midpoint is actually going to be calculated for everything. So it's going to look like this. Left plus right divided by 2. And so now let's do this algorithm again. Is the middle less than the right? It is. So now we don't care about this part of the array, and this is going to be updated to the right pointer now. And our mid pointer is going to be 0 plus 1 over 2, which just ends up being right at the left pointer. And then from here, we can see that the mid is still less than the right, so we get rid of this. And then we're only left with one element. And then once that happens, we know we just want to return the left of the array. So this works for this problem specifically, but let's see if there's any other checks we need to consider for an array that is rotated. So now we have this new array here where the minimum is at the end. So let's see how we can calculate that. So we're going to have our right pointer, our left pointer, and our mid pointer, which is going to be at the 5. So let's see, is our mid less than our right? No. So what do we want to happen? Well, if our mid is not less than our right, we know that our min is going to be on this second half of the array. So what we want to do is move our left pointer over here after the mid. The reason for that is because we know that the mid here is already larger than the element over here. So basically our new formula or algorithm is going to look like if m is less than r, then r is equal to our midpoint, else our left pointer is going to be updated to m plus 1. And then now we use the same formula here that we had for mid, and our mid is going to be 7. Is 7 less than 1? Yes. So we want to update our left pointer again to be mid plus 1, so here. And then we get rid of this part of the array, and then we do this again. And then we update our mid pointer also, and then we check. Is mid less than r? And it's not, because 8 is not less than 1. So now we want to just update our left pointer here, and now we can see that the left and right pointer are equal, and then at this point we would just return whatever is on the left, which would be 1. So what we learned here is that we want to keep looping while left is less than right, and then as soon as left and right are equal, or left is greater than right for some reason, then we just want to return nums at left. And this algorithm runs in logn time because we're using a divide and conquer method, and it is also only going to take constant space because we're only going to use some variables to keep track of where we're at, so just left and our right pointers, and there's no extra data structures needed. And now we can just get into the code. So before we start the code, there's something I need to explain, and it's about overflow. So the way we calculated mid in our examples is by doing mid is equal to left plus right, and then divide that by 2, which makes perfect sense because that is how you find the midpoint. But if we represent it in bits, for example, let's say we're only allowed 2 bits for this problem, meaning that 1 1 represents 3, and that 0 1 would represent 1, and this would equal 1 0 0, which is 4. But this needs 3 bits to be represented, so this will be counted as overflow. And if we calculate mid using left plus right like this, and if we add 1 1 plus 1 0, then we would have 1 1 0, which would cause an overflow error. So the way we're going to actually calculate our mid is by using this formula, because this prevents overflow and still lets us get the mid. It's not very important for this problem, but I think it's something to consider in case your interviewer asks you it. If you want to learn more about overflow, you can just Google it, and I'm sure you'll find a Stack Overflow post that explains it way better than I can. So let's just get into the code now. So to start, we want to have our left pointer start at 0, and our right pointer start at the end of our nums array, which would be the length of nums minus 1. And now we just want to iterate through the whole array as long as left is less than right, like we mentioned in our example. And now we want to calculate our midpoint. So our midpoint is going to be left plus right minus left, and then divide that by 2. So now that we have our midpoint, all we have to do is check, is nums at our midpoint less than nums at our right point? I just realized that my pointers are not named correctly, so I'm just going to fix that real quick. But yeah, we want to update our right pointer so it can be our mid now. Otherwise, we just want to update our left pointer to be equal to mid plus 1. And that's pretty much it. After that, we just can return nums at left because that should be our min. And now we can check to see if it works. Forgot to update these. Hopefully you guys didn't mess that up either. So as you can see, the code is pretty efficient, and now we'll step through the code manually. To start, we just want to initialize our pointers. So our left pointer is going to be 0, and our right pointer is going to be 4, because our nums array length is 5. So now we do the while loop. While left is less than right, and it is currently, then we want to calculate our mid, which is going to be 2. And now we check. Is nums at mid less than nums at right? And if it is, then we want to update our right pointer to be equal to our mid. So let's do that. Right is now going to be 2. So let's just update that here. And we're no longer going to use this part of the array, so I'm just going to cross it out. And now we go to the next iteration. So is left less than right? Yes. And then we calculate our mid. And our mid here is going to be 1, which is pointing to our 5. So is nums at mid less than nums at right? And it is not. 5 is greater than 1. So what we want to do is update our left pointer to be mid plus 1, which is going to be 2. And then now our pointers are pointing to the same exact spot, and we get rid of this part of the array, and we're only left with 1. And then at the end, we just want to return nums at left, which is exactly what this is pointing to, so the code does work. If this video helped you in any way, please like and subscribe. Thanks for watching, and I'll see you in the next video.